Dominant dispersion in single mode fiber. The material dispersion parameter, that is dm, defined by lambda by c into d2 nd lambda square, where n equal to n1 or n2 for the core or cladding. The waveguide dispersion parameter dw can be written as minus of n1 minus n2 by lambda c into v into d2 vb divided by dv square. A profile dispersion parameter dp, which is proportional to d delta d lambda. It may be observed that the dispersion characteristics goes through zero at wavelength 1.27 micrometer, nearly 1.3 micrometer. This zero material dispersion or ZMD point can be shifted anywhere in the wavelength range 1.2 to 1.4 micrometer by addition of suitable dopants. For example, the zero material dispersion point shifts from 1.27 micrometer to approximately 1.37 micrometer as the GeO2 dopant concentration is increased from 0 to 15%. Now, the ZMD point alone does not represent a point of zero path broadening, since the path dispersion is influenced by both waveguide and profile dispersion. So, if we consider different type of dispersion, their variation and with wavelength. So, this is the waveguide part of the dispersion. This is the material part of the dispersion. Okay, and this is the zero dispersion line, this one. So if you add them up, dm and dw, you will get the total dispersion like this. Okay, and you can see right here at lambda 0 you have total dispersion total zero dispersion right here. Okay, but for material dispersion, the zero is right here. Okay, and for a fiber, obviously when we measure the dispersion, we have to consider the total dispersion, not just the material dispersion, right? So though material dispersion is zero right here, but actually when we measure the total dispersion, it will appear right here. Okay, the wavelength at which the first order dispersion is zero, that is lambda 0, may be extended to wavelengths of 1.55 micrometer and beyond by a combination of three techniques, which are called lowering the normalized frequency, that is the V value of the fiber, increasing the relative refractive index difference delta of the fiber, and suitable doping of the silica with germanium. So this allows bandwidth length product for such single mode fibers to be in excess of 100 gigahertz per kilometer, at the slight disadvantage of increased attenuation due to Rayleigh scattering within the doped silica. And that is quite obvious, since you are increasing the dopant, Rayleigh scattering would increase. So total intermodal dispersion, if we consider with the help of the variation due to the radius or the diameter of the core, right? So for 6 micrometer, we have zero dispersion right here. For 5 micrometer, we have zero dispersion right here. And for 4 millimeter, we have zero dispersion right here. So total first order intramodal dispersion as a function of wavelength. So it is showing that it is actually dependent on the code dia.